So, very good morning, students. So, in this video, we are going to discuss complex compound. The subtopic it is the crystal field theory. Crystal field theory. CFT. So, before we going to discuss crystal field theory, first you have to know the limitations of valence bond theory. So, limitations of valence bond theory. Limitations. DP. Because this crystal field theory is also called as a modified valence bond theory. So first you have to know what are the limitations of valence bond theory. So this valence bond theory is not able to explain the color properties of complex compounds. So it fails to explain the color properties of complex compounds. And second, it fails to explain the magnetic variation of magnetic properties, variations in magnetic properties with temperature. It's also one more limitation of valence bond theory, and it also fails to explain the stability of complex compounds. So it fails to explain the stability of complex compounds. It fails to explain the variations in magnetic properties with temperature. Also, it fails to explain the color properties of complex compounds. And next it fails to explain the field strengths of ligands. So, is my audio audible or not? Hello, students. What's clear on that? It fails to explain the field strengths of ligands, whether the ligand is strong field or weak field. Whether the ligand weak field or strong field cannot be explained by this valence bond theory. So it fails to explain the field strengths of ligands, whether the ligand is weak field or strong field. This theory is not explaining this, and also it fails to explain the correct geometries of some complex compounds like Cu NH3 taken 4 times square bracket plus 2, etc. According to VPT, this is sp3 hybridized and tetrahedral geometry, but experimentally it is sp2 hybridized and square planar geometry. So these are the limitations of valence bond theory now. So what about the first one? It fails to explain the color properties of complex compounds. It fails to explain the variations in magnetic properties with temperature. So magnetic properties are varied with increase or decrease in temperature. So that cannot be explained by this valence bond theory. It fails to explain the stability of complex compounds. It fails to explain the field strengths of ligands. So in valence bond theory, some ligands are weak field, some ligands are strong field. That is there, but why that is a strong field and why that is a weak field is not explained VBT now. So therefore, it fails to explain the field strengths of ligands. Whether the ligand is weak field or strong field, that cannot explained by this VBT. It fails to explain the correct geometries of some complex compounds like this copper complex CuNH3 taken 4 times square bracket plus 2. According to VBT, this is a sp3 hybridized molecule and tetrahedral geometry. But experimentally, it was dsp2 and square planar. Therefore, all these are the demerits of valence bond theory. Now, the next it is crystal field theory. Now, this is the CFT. So what is made by this crystal field stabilization theory, CFST or CFT? To explain all the above demerits, to explain the demerits of DBT, Bethe and Black was proposed this theory. This crystal field theory is CFT. To explain the demerits of all the demerits of the VBT theory, Bethe and Blake was proposed this crystal field theory. So in this crystal field theory, there are some assumptions now. So what are the important assumptions? There are many assumptions in this crystal field theory. The first assumption was, according to crystal field theory, according to CFT, all ligands are considered as point charges. This is one of the assumption was made by crystal field theory now. So according to crystal field theory, ligands are considered as point charges. So ligands may be negative ligands, positive ligands. So according to crystal field theory, the positive and negative ligands are considered as point charges. For example, F minus is a point charge, Cl minus, Br minus, all these are the negative ligands. So OH minus, Cn minus, these are considered as what of point charges, and NO plus nitrosonium. So this also considered as what now? These are point charges. These are considered as point charges according to this crystal field theory. This is the important assumption made by crystal field theory. The second one, it is neutral ligands are considered. Neutral ligands are considered as dipoles or point dipoles or dipoles. Point dipoles. This is also very, very important now. For example, neutral ligands. So neutral ligand, it is the water is the neutral ligand. So this is the water, and in water, this is the positively charged species. This is the positively charged one. This is the negatively charged one. So dipole means it will have what now? Two charges, two poles. One is the positive pole and another is the negative pole. Therefore, this neutral ligand is considered as what now? One dipole. And also ammonia. So ammonia is also neutral ligand. So this is also considered as what now? Point charge. So this is the positively charged one. This is the negatively charged one. Positively charged. This is the positively charged one. Therefore, positive negative is there in this species. Therefore, it will acting as what a dipole. Therefore, both are the dipoles. This is the dipole, and it is also dipole or point dipole. This is the second assumption made by this crystal field theory. And the third one, it is assumption made by the crystal field theory is, according to crystal field theory, central metal atoms or central metal cations, central metal atom or central metal cations considered as a cations. This is the most important. Cations. According to crystal field theory, central metal atom or central metal cation is considered as what? Cations. And also ligands are considered as anions. Considered as anions. This is also very important. So this is anion, this is a cation. So central metal cation or central metal atom is considered as what? Cation, and ligands are considered as what? Anions. And one of the most important assumption made by this crystal field theory is, according to valence bond theory, the metal to ligand bond, metal to ligand bond is covalent. Whereas according to CFT, crystal field theory, the metal to ligand bond. So metal to ligand bond is purely ionic or electrostatic. So this is the major assumption made by this crystal field theory now. So according to crystal field theory, the metal ligand bond is covalent. Whereas according to crystal field theory, the metal ligand bond is purely ionic or electrostatic. It means 100% ionic. 100% ionic bond. 100% ionic bond between the metal and ligand. And now this ionic bond was according to crystal field theory, what kind of bond is there now? Metal to ligand bond is purely ionic or electrostatic. That means 100% ionic. Therefore, this ionic bond is arised due to electrostatic forces of attractions. Forces of attractions between the central metal atom or a central metal cation with the ligands. How this ionic bond is arised due to electrostatic force of attraction between the central metal atom or central metal cation with the ligands. So generally, metal is considered as what now? This is the positively charged. Therefore, it is the cationic species. This is the cation. And ligand is considered as what now? In this case, ligand is considered as what? Anions. Therefore, this will have what now? Negative charge. So this is the positively charged species. This is the negatively charged species. Therefore, there will be a electrostatic force of attraction. Due to electrostatic force of attraction, what kind of bond generally generate? Ionic bond will be generated. Therefore, this is the ionic bond. This is the ionic bond. This is the attraction force between the two oppositely charged species. For example, this is the metal atom with positive charge, and this is the ligand. So, for example, O is the OH2. This is the positively charged species. This is the positively charged species. This is the negatively charged atom. So, in between this water, again we have the electrostatic force of attraction. Therefore, it is again ionic bond. Therefore, forces of attractions are two different types. Forces between the metal and ligands are two types. This is the attraction force. Attraction force generally developed between the positive charge of the metal and negative charge of the ligand. and positive charge of the metal and negative charge of the ligand. This is the ligand. This is what ligand? Not neutral ligand, but it considered as what na anion. Why or how this is anion? Because a negative charge is present on the oxygen. Therefore, there will be a attraction between them is called as what na ionic bond. This is the attraction force. Actually, it is what na? This is attraction force. This is what? This is the attraction force. What is meant by attraction force? Attraction, electrostatic force of attraction generally developed between the central metal atom and ligand. Central metal atom and ligand. So positive charge of the central metal atom, positive charge of the central metal atom, and negative charge of the ligand. So in between we have what na? Attraction force. Due to attraction force, we will getting what na? That is ionic bond. So this is the one force of attraction between the central metal atom and ligand. In this central metal atom is the cation, ligand is the anion. So ionic bond is developed between the positive charge of the metal and the negative charge of the ligand. Negative charge of the ligand and positive charge of the metal. Okay, so this is the ionic bond. Next is the second force of attraction. So in addition to this, in addition to this, there are repulsive forces. Repulsive forces between the metal and ligand. Between the metal and ligand. So how this repulsive forces present between the metal and ligand? So it is in between the p orbital electrons of the metal atom and the lone pair electrons of the ligand. Lone pair electrons of the ligand. So there are two different types of bonds. These are the repulsive forces. These are what? Repulsive forces between the metal and ligand. These repulsive forces generally present between the d orbital electrons of the metal atom and lone pair electrons of the ligand. So these are repulsive forces, and the previous one it is the attractive forces. So these are the some. What are these are? These are some assumptions made by crystal field theory. So according to crystal field theory, ligands are considered as point charges. So these are considered as what? Point charges. So neutral ligands are considered as what? Dipole. This is the one dipole. This is also another dipole. Now. So this is the water. In water, we have the two poles. One is the positive pole, another is the negative pole. In ammonia, also positive and negative charges there. Now, therefore, they are considered as dipoles. And next it is according to crystal field theory, central metal atom or central metal cation is considered as what? Cation. So metal atom is considered as what? Cation. Ligand is considered as what? Anion. These are the very, very important. According to valence bond theory, the metal to ligand bond is purely covalent. This is according to valence bond theory, VBT. But according to crystal field theory, the metal ligand bond is purely ionic or electrostatic. Therefore, this ionic bond is arise due to electrostatic force of attractions between the central metal atom with ligands. So this is the central metal atom is considered as what? Cation. This is the ligand is considered as what? Ionic bond, and ionic bond is developed between the positive charge of the metal and negative charge of the ligand. Negative charge of the ligand and positive charge of the metal. There will be an attraction between the two oppositely charged ions. Therefore, you are getting what? That is ionic bond. So now we are going to discuss about the crystal field splitting. So what is meant by crystal field splitting? So crystal field splitting. Crystal field splitting in octahedral complexes. So what is meant by this crystal field splitting? In octahedral complexes. Octahedral complexes. So before we going to discuss this crystal field splitting, first you have to know the shapes of d orbitals. Shapes of d orbitals. So crystal field splitting in octahedral complexes. Before we going to discuss this crystal field splitting in octahedral complexes, first you have to know the shapes or geometries of the d orbitals. So shapes of d orbitals. Shapes of d orbitals. So there are two types of d orbitals. There are two sets of d orbitals. Two sets of d orbitals. One is P2G set of orbitals. P2G set of orbitals. And second, it is the easy set of orbitals. Easy set of orbitals. What are P2G set of orbitals? So in case of P2G set of orbitals, these are dxy, dyz, dzx. These are the P2G set of orbitals. These are the triply generated orbitals, d orbitals, dxy, dyz, dzx. So in this, there are four lobes, and lobes are presented. Lobes are present in between the axes. In between the axes. For example, this is the x-axis, this is the y-axis. This is the x-axis, this is the y-axis. So lobes are present in between the axes at 45 degrees angle. So at 45 degrees angle, lobes are present in between the axes at 45 degrees. At 45 degrees of angle. So this is the electron density, and this is also electron density, and this is the dxy orbital. So lobes are present in between the x and y, in between the x and y, in between the x and y, in between the x and y. This is the x in between the x and y, and this is what now. This is the d orbital. It has two lobes. There are four lobes, and the nodes are for each dxy or dyz, dzx. There are two nodes. One is the xz, yz. For this xz and yz, there is no electron density is present. Therefore, psi square is 0 for this area. So this is the xz area. This is the yz area. So this xz and yz are the nodal planes for this dxy. So this is the y and this is the z. Again the same. These are the d orbitals. So this is also same. This is the dyz. So lobes are present in between the axis only, and this is the two lobes are present in between the axis. Therefore, this is the y. This is not y. X1. This is yz. This is zx. This is x. This is the z. So lobes are present in between the axis in this case only. So lobes are present in between the axis. This is called as what a T2G set of orbitals. And the second, it is a easy set of orbitals. What are easy set of orbitals? These are the second type of orbitals. They are called as easy set. So dx square, y square, and dz square orbitals are collectively called as easy set of orbitals. Yes. So what will be the shape of this easy set of orbitals? So this is the x-axis, this is the y-axis. This is x-axis, this is the y-axis. So lobes are present. There are four lobes. Those four lobes are present on the axis. So electron density is present on the axis only. So here angle is 0 now. So this is what the dx square y square orbital. So lobes are present on the axis, and this is the dz square orbital. This is the dz square. This is z axis. This is z axis, and there is a concentric ring present at xy plane. This is at xy plane, and these two lobes are on z axis. On z axis. So these are the easy set of orbitals. There are 5d orbitals dividing into two sets. One is the T to G set and another is the easy set. T to G set orbitals are dxy, dyz, dzx, and in these there are four lobes. Lobes are present in between the axes. So xy axis, lobe is present in between the xy. Lobes are present in between the yz. Lobes are present in between the xz. This is the second type, easy set of orbitals. These are dx square, y square, and dz square orbital. Lobes are present on the axis, along the axis, along the axis. This is the along the xy axis. That's why this is dx square, y square. This is the dz square. In this, along the z-axis, there are two lobes, and on the xy plane, we have one ring. This is dz square orbital. So this is about what the shapes of d orbitals. So now let us move to this crystal phase splitting in octahedral complexes. So why crystal phase splitting is arise? So what is meant by crystal field splitting actually? The crystal field splitting. Crystal field splitting in octahedral. In octahedral complex. In octahedral complexes. Octahedral complexes. Actually, this is the these are the lobes present on the xy axis. This is x axis, this is the y axis. Suppose this is the central metal atom d orbital. This is the dx square y square. Dx square y square or dz square orbitals, etc. So that means easy set of orbitals, you write. For easy set of orbitals. Easy set of orbitals. For easy set of orbitals, suppose this is the ligand. This is the ligand and this is the central metal atom. This is a central metal atom d orbital and this is the ligand. Okay. So now this is the ligand with an electron pair donor, and these are the d orbitals of what type? This is easy set of orbitals. So this is on what now? X-axis. So this is the ligand. So this ligand is approaching along the axis only in this case. So the electrons of this ligand, lone pair electrons of this ligand, and d orbital electrons of this metal atom. So when ligand is approaching along the easy set of orbitals axis, repulsion increases. So repulsions increases. Therefore, energy also increases in this case. So when ligands approaching to the easy set of orbitals, there will be a repulsion between them. Due to that, repulsions increases, energy decreases. Whereas in the case of T to the set of orbitals, suppose this is the ligand. This is what now? This is the ligand. This is the ligand orbital. This is the ligand orbital. Ligand. And this is what now? This is T to the set of orbitals. This is the T to the set of orbitals. T to the set of orbitals. When ligands approaching T to the set of orbitals along this axis, So in between these lobes, there are no orbitals present in T to the set of orbitals. Therefore, in this case, repulsions less. Therefore, energy decreases. Energy decreases in this case. Therefore, ligands when approaching easy set of orbitals along the axis, repulsions usually increases. Therefore, energy will be increased. Whereas ligands, when approaching to T2G set of orbitals in between the axis of the T2G, repulsions generally or usually decrease and energy will also decrease. So this is the phenomenon generally present in the crystal field splitting. Now, crystal field splitting in octahedral complexes. So octahedral complex generally what will be the formula na octahedral complex? So Ml6 plus or minus N. So Ml6 plus or minus N is the complex compound formula of octahedral species. M is the central atom and there are 6 ligands coordinating with the central metal atom. Therefore, this is the Ml6. It is an octahedral complex. Now, so in octahedral complex, how d orbitals splitting taking place. So these are the 5d degenerate orbitals. 5d degenerate orbitals. These are the 5d degenerate orbitals of the central atom. Degenerate orbitals. 5d degenerate orbitals of the central atom. Of the central atom. This is energy increasing order. So without any ligand is present in the along with the central atom, these are the degenerate orbitals because degenerate means equal energy. These 5d orbitals have the same energy orbitals, same energy. So now the central atom is present without any ligand. At that place, at that time, the degenerate orbitals are these. Now, when ligands approaching to this central atom symmetrically and spherically, field of the ligand when it is approaching, so their energy increasing, but degeneracy is not changing. Here we have the degeneracy is there now. In this case, degeneracy is there. This is a hypothetical concept. And hypothetical concept. Hypothetically, when ligands approaching to this d orbitals symmetrically and spherically. So when ligands approaching symmetrically and spherically, the d orbital's energy increases, but degeneracy, it is also degeneracy is there now in this case. Degeneracy is maintained in this case. Here also we have the degeneracy, here also we have the degeneracy. When ligands approaching to the metal cation after the formation, the degeneracy of the central atom d orbitals, this is the EZ set, this is the T2G set. So these are there are 2 EZ orbitals. In this case, there are 3 T2G orbitals. So what is this now? This is actually this is without any ligand. All the degenerate orbitals are there now. But when ligands approaching symmetrically, spherically, this is a hypothetical concept. So always ligands approaching not in symmetrical and spherical. But if you assume ligands approaching spherically or spherically and symmetrically, again we have the degeneracy. There is no change in the degeneracy of these 5d degenerate orbitals. These are the degeneracy 5d degenerate orbitals now. But ligands not approaching symmetrical and spherically, therefore these 5d degenerate orbitals losing its degeneracy. Therefore, in that way, These 5d degenerate orbitals can be split into two energy levels. This is called as what now? Crystal field splitting. This is the crystal field splitting. Crystal field splitting. Crystal field splitting in octahedral complexes. In octahedral complexes. So what is crystal field splitting? The crystal field splitting in octahedral complexes, the energy barrier between the higher energy EZ and the lower energy T2G is the delta naught. This is the Barry center. Barry center. So this is the Barry center. This is the energy between the energy difference between the higher energy EZ and the lower energy T2G orbitals. And the energy gap between this delta naught and the higher energy EZ is plus 0.6 delta naught. This is the energy gap between the delta naught and lower energy T2G. It is minus 0.4 delta naught. Or also you can write it as this is also equal to minus 2 by 5 delta naught. This is equals to plus 3 by 5 delta naught. The energy between these two is 3 by 5 delta naught. The energy between these two is minus 2 by 5 delta naught. This is the lower energy orbital, this is the higher energy orbital. The energy gap between them it is delta naught. Delta naught is the 10 dq. It is also equal to 10 dq. Delta naught is equal to 10 dq. Delta naught is the barycenter, that is also equal to crystal field stabilization energy. So this is without any ligand. These are the 5d degenerate orbitals. This is an hypothetical concept. Whenever ligand approaching symmetrically and spherically, there will be no change in their degeneracy, but their energy is increasing. Their energy is increasing, but all these d5 orbitals have the same degeneracy or same energy. But ligands approaching these d orbitals not in spherical and symmetrical field. Therefore, their energies this is the EZ and this is the T2G. These d orbitals energy is varied from higher to lower and lower to higher. So whatever the this will be depending upon the crystal field. This will depending on the geometries of the complex compounds. So this is the crystal field splitting in octahedral complexes. So actually, what will happen here? So what is mean by crystal field splitting? Again, I will explain now. Actually, the metal d orbital, the metal d orbital has degeneracy. Degeneracy means all the d orbitals having same energy. The metal d orbital has degeneracy. So when metal atom is dissolved or placed in ligand solution. In ligand solution, metal d orbital has degeneracy. When metal atom is dissolved or placed in ligand solution, these d orbitals of central metal atom lose its degeneracy. The metal d orbital actually it has what the degeneracy. When metal atom is dissolved or placed in ligand solution, the d orbitals of central metal atom lose its degeneracy. Due to, as a result of this, As a result of this, d orbitals can be split into two groups. One is T2Z and another is the TCB. So due to this only, one is easy. As a result of this, d orbitals can be split into two groups. One is the T2Z and another is the EZ. One is T2Z and another is the EZ. So what is the reason behind this now? What will be the reason why the degeneracy of the central atom d orbitals? The d orbitals of central atom, why it losing its degeneracy? Because of when ligands approaching the central metal atom, there will be a repulsive forces between the d orbital electrons and lone pair electrons of ligands. So that's why d orbitals of central atom is losing its degeneracy. This is called as what? The crystal field splitting. This is called as what? Crystal field splitting. So this is the crystal field splitting. Actually, this can be defined as the n-1 d orbitals. The degeneracy of n-1 d orbitals. n-1 d orbitals of central metal atom is not maintained during the formation of complex compound. During the formation of complex compound is called as crystal field splitting. Crystal field splitting. This is called as what? Crystal field splitting. So the degeneracy of n-1 d in case of D first series 3D series, the degeneracy of 3D orbitals of central atom is not maintained during the formation of complex compound. This is called as what? Crystal field splitting. So how this is now? Actually we already discussed this one. These are the 5D degenerate orbitals without any ligand is present. At that time, these are the 5D degenerate orbitals. But in the presence of ligands, if you assume ligands approaching spherically, equally to this d orbitals, their energy increases. But degeneracy, there will be no change in the degeneracy of these 5D orbitals. But here degeneracy is changing. Degeneracy is changing means these 5D degenerate orbitals split into two energy levels. One is the EZ and another is the T2Z. So why this is happening? So actually in ML6 what will happen in ML6? So actually this is the central atom and these are the four ligands. There are four ligands in one plane. This is in one plane. This is in one plane and this is the ligand is above to the plane and this is the ligand is below to the plane now. So actually this is in what direction now? This is the x-axis. This is x-axis. This is y-axis. This is x-axis. This is x-axis. This is the y-axis. is the y-axis and this is the z-axis, and this is the z-axis. So we have two different types of ligands now. We have two different types of d orbitals. So the d orbitals which are oriented along the axis, what they are now, they are p to this easy set of orbitals. Actually, so on x and y we have a these are the ligands are present on x and y. There are four ligands in this. Those four ligands are present on x and y axis. So on the x and y we have one orbital in d orbitals. In the d subshell, one orbital is there now, that is the dx square y square, which is present on the xy axis. Lobes are present on the xy axis. The d orbitals which are present on the axis experienced greater repulsions from these ligands. So there are four ligands. This one, this one, this one, this one. These four ligands are present on the axis, x-axis, y-axis, x-axis, y-axis. But these ligands also approaching this central atom along that way only. Therefore, there will be a repulsion between the d orbital electrons of the metal and lone pair electrons of this ligand. Therefore, repulsion increasing in this case. Therefore, energy will also increasing. Therefore, their energy is increasing in this case. Therefore, easy orbital's energy is more in this case. But this is the d. This is also what not. This is the z-axis. On the z-axis, you have two ligands. So ligands which are the d orbitals which are oriented along the z-axis. That is the dz square. Dz square and this ligand. There will be a repulsion between them. Therefore, their energy will also increase. Therefore, easy set of orbitals energy is more in case of octahedral complexes compared to this T to G orbitals, because T to G orbitals are what now? This is the dxy, this is dyz, this is dzx. So these orbitals lobes are in between the axis only, but ligands in octahedral complexes never approaching in between the axis. That's why their energy decreases, because less repulsions between them now. So dxy, dyz, dzx with the ligands, repulsions generally less. Therefore, energy will also lower. Whereas in the case of dx square y square, ligands approaching xy axis, ligands approaching xy axis, ligands approaching xy axis. So, the d orbitals which are oriented in between, the d orbitals which are oriented along the axis is near to the orbitals of the ligands. Therefore, there will be a greater repulsion. Therefore, easy orbitals experience greater repulsions from the ligands. Therefore, their energy increasing, whereas T to G orbitals experience lesser repulsions as they are approaching with ligands in between the axis. Therefore, their energy decrease because repulsion between them is very less. Therefore, this is the this is the splitting in octahedral complexes. What is meant by this? And the next it is after this crystal field spreading in octahedral complexes. The next point it is the pairing energy now. So, what is meant by the crystal field stabilization energy actually? Crystal field stabilization energy. Crystal field stabilization energy. So, what is meant by crystal field stabilization energy now? The stabilization energy gained by the complex compound. So, what is this crystal field stabilization energy? The stabilization energy gained. Stabilization energy gained by the complex. Gained by the complex by filling electrons into lower energy 2Tz orbitals of octahedral complex. So this is the CFSE. The stabilization energy gained by the complex compound by the filling of electrons into lower energy T2G orbitals of octahedral complexes. So in case of octahedral complexes, CFSE it is equals to minus 0.4 into T2G electrons plus 0.6 into Tg electrons. So delta naught plus pairing energy. This is the pairing energy. So what is meant by pairing energy? So this can also be represented by another way. So CFSE is equals to minus, in case of 0.4 we have water, this is minus 2.5 into T2Z electrons. T2Z electrons plus this is plus 3 by 5 into EZ electrons to delta naught plus pairing energy. So here one thing, what is the pairing energy? So what is meant by this pairing energy? Pairing energy. So it is the amount of energy. Is the amount of energy required. Is the amount of energy required to fill the two electrons. Fill the two electrons in a single orbital. In a single orbital. So amount of energy required to fill the two electrons in a single orbital. For example, so the total pairing energy is equals to delta naught plus m into p. Total pairing energy is equal to pairing energy into m into p. What is pairing energy? So total pairing energy is equal not this one, not this one. No. M into p. So where m is the number of paired electrons and p is the pairing energy. So using is the amount of energy required to fill the two electrons in a single orbital. That is total pairing energy is equal to m into p, where m is the number of paired electrons, p is the pairing energy. Suppose using the relative energies of delta naught and pairing energy spin state of complex can be measured. So how this can be helpful to calculate the spin state of the complex? Suppose there are two cases now. So case one, if delta naught is greater than the P, so this will happen in the presence of strong field ligands. Presence of strong field ligands. So what will happen? Strong field ligands. Presence of strong field ligands. Suppose these are the 5D degenerate orbitals. These are the 5D degenerate orbitals. In the presence of strong field. The presence of what will happen now? This is the crystal field splitting. In case of octahedral, the lower energy is the T2G and higher energy is the EZ. This is the EZ set. Suppose if the energy gap is very large, if delta naught, this is the delta naught, this is the delta naught, this is the crystal field splitting in octahedral complex. This can be represented by delta naught. If delta naught is this gap, this the energy, this is the energy higher, this is the lower energy. If the energy gap between them it is very high, then the pairing energy, this is very high. Therefore, electrons filling taking place like this only. So 1, 2, 3, 4, 5. This is the sixth one. This is the seventh one. This is the eighth, ninth, 10th. So these 10 electrons filling is taking place like this only. So 1, 2, 3, 4, 5, 6. This is the 7. This is the 8. This is the 9. This is the 10. So this kind of distribution of electrons taking place when delta naught is greater than the P. When delta naught is greater than the P, this kind of filling of electrons taking place in the EZ and T2G set of orbitals because this gap is very high. Therefore, pairing taking place in the lower energy followed by the higher energy. So this is delta naught is greater than the P. For example, if you take the only D5, suppose if there are 5 electrons in the D5. So these 5 electrons splitting into lower energy T2G and higher energy EZ in this area. So 1, 2, 3. This is the fourth one. This is the fifth one. So in the lower energy we have the 2 electrons. In a single orbital we have the 2 electrons. In the single electrons we have the 2 orbital. In the single orbital we have the 2 electrons. How many there are now? Actually 1, 2, 3, 4, 5. So this is the filling of electrons in D5. Therefore, because why it is happening now? Because delta naught is greater than the P. This gap is very high. This gap is very high. Therefore, pairing takes place in the lower energy, followed by the higher energy now. So this will happen in the presence of strong field ligands. So in the presence of strong field ligands, electron distribution taking place again is to Hund's rule. This is happening again is to happening again is to again is to Hund's rule. Again is to Hund's rule. So the presence of strong field ligands, electron distribution taking place again is to Hund's rule. So if you take the D5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These 5d degenerate orbital electrons split into like this only now. So in the lower energy we have what now? 1, 2, 3, again 4, 5 in this only, not in this. Because delta naught, this is the CFSE is very large. Therefore, pairing takes place in the lower energy. This is happening against to Hund's rule only now. So this is in presence of strong field ligands. So strong field ligands generally electron distribution taking place against to Hund's rule. We already seen in the VBT theory also. And the next it is if delta naught is less than the case 2. Case 2 is if delta naught is less than the pairing energy. Here pairing energy is more, CFSE is very slow, very small. So this is the 5d degenerate orbitals. These are the 5 degenerate orbitals, and here the energy gap between them it is very small. Energy gap between this one is very small. So delta naught is small. Delta naught is very small. Therefore, pairing cannot take place. So this is 1, 2, 3, 4, 5. This is the sixth one, this is the seventh one, this is the eighth one, this is the ninth one, the 8, 9, and this is the 10. So there are 10 electrons in the 5d degenerate orbitals. 5d degenerate orbitals, there are 10 electrons. And here, in the presence of this is in the presence of weak field ligands. In the presence of weak field ligands, what will happen now? The presence of weak field ligands, electron distribution taking place according to Hund's rule, because this delta naught is very small. Therefore, electron jumps from lower to higher very easy. Therefore, pairing not taking place. So 1, 2, 3. This is the fourth one. This is the fifth one. Again, pairing starts. Sixth, seventh, eighth. This is the ninth. This is the 10th. So here delta naught is very small. Therefore, pairing here pairing energy is very large. Therefore, no pairing occur. No pairing occur. So 1, 2, 3, 4, 5, then 6th, 7th, 8th, 9th, 10th. Here delta naught is very small, therefore electrons can jump from lower to higher very easy. This will happen in the presence of weak field ligands only. So electron tends to fill in the not fill in the lower. So this is the case too. If delta naught is less than P, that in the presence of weak field ligands it is happening. So here, for example, if you take the D5, so this is the D5. So this is the splitting in the presence of weak field ligands. In the presence of weak field ligand, so this is the T2G, EG. This is the EG. This is the T2G. So presence of weak field ligands. Presence of weak field ligands. Presence of weak field ligands. Presence of weak field ligand. So for D5, 1, 2, 3, 4, 5, D5. So the presence of weak field like this now 1, 2, 3, this is the fourth one, this is the fifth one. So this will happen in the presence of weak field ligand. Here spin is very high. Therefore, spin state of complex compound can be calculated with this conditions. So if delta naught less than P, this is the low spin or high spin. So this is the high spin complex is formed. High spin complex compound is formed in the presence of weak field ligands. The presence of weak field ligands, high spin. So this is the single electron, this also single electron, this also single electron, this also single electron, this also single electron. So single electrons are more, therefore that will be the high spin complex. So in the here what now in D5, single electrons, only one single electron is there now. Therefore this is the low spin complex. Low spin complex this is. Low spin complex. Therefore spin state using the relative energies of delta naught and pairing energies, spin state of complex compound can be measured. Case 1 what now? This is the if delta naught is greater than P, the higher energy Eg, this is the lower energy T2G. The energy gap between them it is very large. So in this case, what will happen? Electrons distribution taking place against to Hund's rule. Electrons tends to fill in the lower energy E to T2Z only. After that only easy. So for example, D5, so 1, 2, 3, and then fourth one in this only, fifth one in this only. Therefore, only one single electron is there now. Therefore, it is a low spin complex now. So why it is happening now? If the energy gap between the higher energy EZ, lower energy T2G is very large. In that condition, we have what now? Low spin complex compounds are forming. So this is the relative energies of delta naught, and so this is the case 2 now. So after this, we have some questions regarding this now. For example, write an electron configuration of T2G and EZ. Write an electron configuration. Write an electron configuration of T2G and EZ for D4 and D7 complexes. D7 complexes. Our question. For example, presence of strong field ligands. Presence of strong field ligands are D4. So D4 means there are 5 electrons. 4 electrons in this one. So 1, 2, 3, 4, and 5. So these 5 D generate orbitals. Only 4 electrons. So this is the 4 electrons. The lower energy T2G, the higher energy EZ. So in between we have what now? This is the carry center. Delta naught is the what now that is, this is the stabilization energy in complex compounds. So here is in the presence of strong field ligands, what will happen now? Electron distribution taking place again is Hund's rule. So 1, 2, 3, this is the fourth. Therefore, what in T2G we have what electron configuration? T2G 4 and EZ 0 in this case now. T2G 4 and EZ 0. So number of unpaired electrons 2. Number of unpaired electrons 2 now. So these are the number of unpaired electrons. Number of unpaired electrons 2. If unpaired electrons there, what will happen now? This will be the paramagnetic. Suppose in presence of weak field, what will happen now? So presence of weak field ligands. Presence of weak field ligand, what will happen now? So D4. D4. So 1, 2, 3, 4. This will split into what? So 1, 2, 3. This is in presence of weak field. This is the EZ and this is the T2G. So only one electron. This is the fourth electron. So 1, 2, 3 and 4. So this type of electron distribution taking place in presence of strong field. This is the weak field. So here we have what now? Delta naught is lower than the pairing energy. So here pairing energy is very large, but here pairing energy is lesser. This is what now? Delta naught is greater than P in this case. In this case, what now? Delta naught is less than the pairing energy. So delta naught is less than pairing energy. Therefore, this is in presence of weak field. This is in presence of strong field. The number of unpaired electrons are what now? Number of unpaired electrons 4. Number of unpaired electrons 4. So this is number of unpaired electrons 4 now in this case. Therefore, it is also paramagnetic. This is the paramagnetic. The number of unpaired electrons 2 now. So suppose if you take the D7 now. So what about the D7 now? So for D7 electron configuration. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. This is the sixth one. This is the seventh one. This is the eighth one. Only 7 now. So only 7. One, two, three, fourth one, fifth one, sixth one, seventh one. So there are D7 in this case. So these 5D degenerate are split into energy levels, different energy levels. This is in presence of strong field ligand. Strong field ligand, what will happen to strong field ligand? So 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is the seventh one. So T2G6. So what will happen here? T2G6 is 1 only. T2G6 is 1. Whereas in this case, what not D7? D7. So 1, 2, 3, 4, 5, 6 to 7. This is the D7. In the presence of weak field, what now? Presence of weak field. Presence of weak field ligand. What will happen? Splitting taking place. These are the two energy levels, EZ and T2G. The presence of what now? This one? Weak field ligand. Therefore, electron distribution taking place. This is the 1, the 2, the 3, the 4th, the 5th one, the 6th one, this is the 7th one. So what will happen here? T2G 1, 2, 3, 4, 5. T2G 5, EZ2, this one. T2G 5, EZ2. So in T2G we have how many unpaired electrons now? 3 unpaired electrons in this case. 3 unpaired electrons. So this is unpaired, this is unpaired, this is unpaired. So number of unpaired electrons 3. This is also what now? Paramagnetic. And here number of unpaired electrons are only how many now? Only 1. Number of unpaired electrons only 1 in this case. So number of unpaired electrons in this 1, number of unpaired electrons in this 3. Next, after this we have the next series. We have the one more question now, that is in case of K for FeCN6, write electron configuration. Write electron configuration in terms of configuration of metal atom in terms of terms of T2Z and EZ. T2Z and EZ. So one is the K4FeCN6. K4FeCN6. It's a complex compound. And one more, that is the FeH2O taken 6. Second, it is FeH2O taken 6 square bracket plus 2. So these are the two complex compounds. Now you calculate the electron configuration of the central atom iron in terms of T2Z and ECN. So in this central atom is the iron. So iron is the central atom. So central metal atom is the iron. So iron electron configuration is what now? Argon 3d6 4s2. 3d6 4s2. And but oxidation state of iron is what now? Oxidation state of iron in this case is what now? You consider this as x. This is plus 4 plus x. You consider this is the x. This is the first A plus 1 into 4 plus 4. This is you consider this as x. And there are 6 Cn minus ligands. Each one is minus 1. Therefore, minus 6 it is equal to 0. So sum of oxidation numbers of all the elements must be equal to 0. So x minus 2 is equal to 0. X is equal to what now? Plus 2. So x is equal to plus 2. Therefore, plus 2 oxidation state is what now? Plus 2 oxidation state. In plus 2 oxidation state, electron configuration is what? Argon 3d6 only. Argon 3d6. So number of d orbital electrons are 6. So there are 6 electrons in the d shells. D orbitals. So 1, 2, 3, 4, 5. This is the 6th. So these d orbital electrons split into what now? Different energy levels. In case of octahedral, this is the octahedral complex. Coordination number is 6 is the octahedral. So these are the, this is T2Z and this is the EZ. But here Cn minus is a strong field ligand. So Cn minus is a strong field ligand. Strong field ligand. So strong field ligand means delta naught is greater than the P. This energy gap will be maximum. This energy gap will be maximum. Therefore, pairing energy gap is more. Therefore, pairing will taking place. Therefore, because of it is a strong field ligand. So therefore, electron distribution taking place like this only. So 1, 2, 3, 4, and this is the 5, and this is the 6. Therefore, this is the T2G6, EG0. T2G6, EG0. So number of unpaired electrons 0. Number of unpaired electrons what now? Number of unpaired electrons 0. So therefore it is the diamagnetic. Number of unpaired electrons is equal to 0. Therefore it is the diamagnetic. So the electron configuration in terms of iron plus 2 is T2G6 EG0. And the second it is FeS2O taken 6 square bracket plus 2. So this is the neutral ligand. Therefore iron oxidation number is the plus 2 in this case. So iron oxidation number is the plus 2 in this case. But H2O is a weak field ligand. But H2O is a weak field ligand. H2O is a weak field ligand. Therefore, electron distribution according to Hund's rule only. So Fe plus 2 electron configuration is what now? This is argon 3d6 only. Argon 3d6. So D6. D6 means what? There are 6 electrons in the 1, 2, 3, 4, 5, or this is the 6th. This is the 6th. So in the presence of weak field ligand, what will happen? Presence of H2O ligand. Presence of H2O ligand. It is a weak field ligand. This is a weak field ligand. So presence of weak field ligand, what will happen? Electron distribution taking place according to Hund's rule. So 1, 2, 3, 4, 5. And then this is the 6th one. The number of unpaired electrons are 6. This is the one single electron, this is single electron, this is single electron, this is single electron. So number of unpaired electrons 4. 4 are unpaired electrons. Unpaired electrons present in the d subshell of the metal, that will be the paramagnetic. So this is the paramagnetic. So write an electron configuration of the metal atom in terms of T2G Eg in this manner. So this is the K for FeCN6. Here we have the Fe plus 2, but Cn is the strong field ligand. But here H2O is the weak field ligand. So presence of weak field and presence of strong field electron distribution is different now. Therefore, in this we have what not T2G6 Eg0. This is the T2G6 Eg0. But here we have what not T2G4 1, 2, 3, 4, 5, 6. T2G4 Eg2. This is the electron configuration. This is the variation in the presence of weak field and strong field ligands. So after this we are going to calculate calculating the distribution of electrons and their crystal field stabilization energy. So CFSE actually it is equal to what now in case of octahedral complex. In case of octahedral complex, what now this is minus 0.4 into T2G electrons plus 0.6 into Eg electrons into delta naught plus pairing energy. This is the formula for the crystal field splitting energy. What is meant by crystal field stabilization energy? Now it is the amount of what is crystal field stabilization energy? The stabilization energy gained by the electrons. The stabilization energy gained by the complex compound by the filling of electrons in the lower energy orbital of the octahedral. So that will be the CFSE. So CFSE is equal to minus 0.4 into T2G electrons plus 0.6 into Eg electrons. Suppose so d orbital electrons from D1 to D10. So this is electron configuration in terms of T2G and Eg. The presence of strong field ligands. And this one is the CFSE. CFSE is equal to what now? Is only in presence of strong field ligands. So what is strong field ligand? For example, you take the D1. Even electron configuration. Presence of strong field, what now? This is T2G1, Eg0. Only one electron is there, not T2G1, Eg0. And here also we have a electron configuration in terms of T2G and Eg. T2G and Eg. And then CFSE. This is the D1. So in case of D1, in the presence of strong field ligand, this is in presence of weak field ligands. So presence of weak field ligands. What will happen in this case now? So d orbital. So D1, T2G1, Eg0. So D2, T2G2, Eg0. D3, T2G3. So all the electrons. This is according to against Hund's rule. T3, T4, T2G4, Eg0. T5, T2G5, Eg0. D6, T2G6, Eg0. Next D7, T2G6, Eg1. D8, T2G6, Eg2. D9, T2G6, Eg2, Eg3. D10. So what not? T2G7, T2G6, Eg4. So this is the electron configuration in presence of strong field ligands of D1 to D10. And what about the CFSE values? So what about the CFSE values in this case? So CFSE, what the principle of minus 0.4 into T2G electrons 1 plus 0.6 into Eg, 0.6 Eg electrons 0. This is the delta naught plus number of pairing electrons 0 now. So there is no pairing electrons, no two electrons in a single orbital in this case now. Therefore, this is equal to 0. Therefore, what will happen now? Minus 0.4 delta naught. So this whole is what now? Minus 0.4 delta naught. Minus 0.4 delta naught. And D2 what now? Minus 0.4. Minus 0.4 into 2 plus 0.6 into 0 into delta naught plus again number of pairing electrons 0. No two electrons in a single orbital in this case also. Therefore, this pairing energy is equal to what? M into P. M into P, where M is the number of pairing electrons and P is the pairing energy. Number of paired electrons. Number of paired electrons into P, that is equal to total pairing energy. So minus 0.4 into 2 plus 0.6 into 0 into delta naught into 0. So this is minus 0.8. So minus 0.8 delta naught. So in case of T2G3, what now? This is minus 0.4 into 3 plus 0.6 into 0 into delta naught plus 0. Here no two electrons. Here also we have what now? No two electrons in a single orbital. In all these three cases also. Here also we have what now? In T2G4 minus 0.4 into 4 plus 0.6 into 0 again this electron 0 into delta naught plus 1 orbital of this T2Z with 2 electrons there now. Therefore 1p number of paired electrons 1 into pairing energy. So 1p. This is the total energy, total CFS energy for this T4. This is a D4. Yes, D5 is what now? This is number of T2Z what now? 5 electrons. So minus 0.4 into 5 plus 0.6 into 0. In this we have 0 electrons, in this we have what now? 5 electrons. So minus 0.4 into 5. Our principal minus 0.4 into T2Z electrons, minus 0.4 into 5 electrons, plus 0.6 into Eg electrons 0, 0.6 into Eg electrons. So now it is 0. And in T2G5, how many number of electrons are paired? How many number of shells are paired with electrons? So 2 shells, therefore 2. So therefore this is what? 2 into P, 2P. In D6 what? How many electrons? Minus 0.4 into 6 plus 0.6 into 0 into delta naught plus 3 into P, because 3 shells with 2 electrons now. So in D7 what now? In D7 minus 0.4 into 6. Here we have what now? Easy electron. Therefore 0.6 into 1 into delta naught. Again we have 3 shells with 2 electrons. Therefore 3 into P. This is the total pairing energy. And in D8 what now? In D8 we have what? Number of minus 0.4 into 2, minus 0.4 into 6 and 0.6 into 2 into delta naught plus 3 into P again it is. Because in this we have how many shells with 2 electrons? 3 shells with 2 electrons. In EZ2 means there are 2 subshells. Each subshell is with single electron. Therefore EZ2 means 0 paired electrons. Therefore only 3 into P only now. So in D9 we have what now? In T2G6 is 0. So minus 0.4 into 6 plus 0.6 into 3 into delta naught plus how many? 4 are electrons, 4 subshells with 2 electrons now. That's why 4 into P. In D10 we have what now? Minus 0.4 into 6 plus 0.6 into 4 into delta naught plus in this we have 3, in this we have 2 are paired. Therefore 5P. So this is the total CFSE energy for the DR bus with D1 to D10. D1 to D10. Their total energy it is equal to minus 0.4 into T2G electrons plus 0.6 into EG electrons into delta naught plus pairing energy. So pairing energy is equal to what now? M into P, where M is the number of electron pairs into pairing energy. So pairing energy is the P in this case. Here no two electrons, which is shell, therefore 0. Here also no two electrons in a single orbital. Here also no two electrons in a single orbital. In this also one shell is with two electrons. That's why 1 into P. In this way, what now? Two shells with two shells with two electrons. That's why this is 2P. In this way, three shells with two electrons. Therefore, number of paired electrons 3. So in this way, what now? 3 into P. Here also we have 3 into P. Here we have what now? 3 in T2G and 1 in EZ. Because EZ having what now? 3 electrons. Therefore, totally 4 into P. P to the 6 is 4 minus 0.4 into 6 plus 4 into 0.6 into delta naught plus there are in this we have 3 shells with two electrons. In this we have 2 shells with 2 electrons. Therefore, totally 5 are the shared pair electrons. Not shared pair electrons, they are paired electrons. So next it is with weak field ligands now. So with D1 electron configuration, T2Z1 is 0. With weak field ligands, electron distribution taking place according to Hund's rule. So in presence of weak field ligand, this is the electron configuration in terms of T2Z EZ in the presence of weak field ligand. So in the presence of weak field ligand, electron distribution generally taking place according to Hund's rule. So one electron in this T2Z1 and EZ0. Next D2 what now? T2Z2 EZ0. Next electron enters into T2G, T2G3 EZ. Next electron enters into, this is in case of 3 only now. So now this is the fourth one, T2G 3 EZ1. This is happening in the weak field ligand now. Next is what now? T2G 3 EZ2. Next electron enters into lower energy T2G, that is T2G4 EZ2. Next electron enters into T2G 5 EZ2. Next electron enters into lower energy T2G, T2G6 EZ2. Next electron already T2G completely filled, therefore T2G6 EZ3. Next electron T2G6 EZ4. So this is the distribution of electron taking place in presence of weak field ligands. So in the simple way, again we have to calculate the CFSE for this one also. So minus 0.4 into 1 plus 0 into 0.6 into delta 0 plus 0 into P. So for this we are calculating now. So CFSE is equal to what for this T2G1 same minus 0.4 into 1 minus 0.4 into 1 plus 0.6 into 0 electrons in the EZ into delta naught plus number of pairing electrons 0 into P. This is the pairing energy now, total pairing energy. Next in this what now? Minus 0.4 into 2. Minus 0.4 into 2, this one. Plus 0.6 into 0 into delta naught. Plus 0 into P again. In this way what now? Minus 0.4 into 3 plus 0.6 into 0 into delta naught. Plus 0 into P again. So in this way what now? Minus 0.4 into 3 plus 0.6 into 1 into delta naught plus 0 into P. In this way what now? Minus 0.4 into 3, T2G electrons 3, these electrons 2. So 0.6 into 2 into delta naught plus is there any pairing electrons? 0 pairing electrons. Therefore 0 into P again. And here we have one electron is paired in the T2G. Therefore minus 0.4 into 4 plus 0.6 into 2 into delta naught plus how many number of pairing electrons now? One number. So 1 into P. So here how many electrons pairing now? So minus 0.4 into 5 plus 0.6 into 2 into delta naught plus number of pairing electrons. How many now? They are 2. 2 into P. This how many number of unpaired, how many electrons paired now? 3 are paired. Therefore, minus 0.4 into 6 T2 electrons plus 2.6 into 2 electrons into delta naught plus 3 into P. So in this way, what now? Minus 0.4 into 6 plus 3 into 0.6 into delta naught plus how many are now? 4 are paired. So therefore 4 into P, the pairing energy. So in this way, what now? Minus 0.4 into 6. Minus 0.4 into 6, 4 into 0.6 into delta naught plus 5 into Q. So this is the CFSE. So once you calculate these values, D1, D2, D3 and D8, D9, D10. D1, D2, D3, D8, D9, D10 having same CFSE values. Therefore, CFSE is independent on the nature of field strength of the ligands in this case now. So D1, this D1, D2, D3 and D8, D9 and D10. So D1, D2, D3, D8, D9, D10 have a similar CFSE values in case of weak field and strong field. Both the presence of weak and strong fields, these values are similar. Their CFSE values are same. If you calculate these values, you will get the similar values for the D1, D2, D3 in the presence of strong field, in the presence of weak field. For D2 also, you will get some value, the same value will appear in the weak field also. Therefore, D1, D2, D3 in the presence of D1, D2, D3, D8, D9, D10 will have a similar values in the presence of weak field as well as strong field ligands. Therefore, CFSE is independent on the nature of field strengths of ligands. Whether the presence of strong field ligand the same value or in the presence of weak field ligand also you will get the same value. Therefore, D1, D2, D3, D8, D9, D10. These electron configurations will show the similar electron configurations, not similar electron configurations, similar CFSE values in the presence of weak field as well as strong field ligands. But D4, D5, D6, D4, D5, D6. D4, D5, D6 will not show the similar CFSE values in the presence of weak field and strong field. The D5, D6, D7 and D4. These electron configurations will show one value in the presence of strong field and another value in the presence of weak field. D5 will show one value in the strong field ligand and one value in the weak field ligand. D6 and D7 also will show the one value in the presence of strong field ligand, one value in the presence of weak field ligand. Therefore, their CFSE will depends upon the field strengths of ligands. If you calculate the CFSE in the presence of strong field ligand, you will get one value for D4, another value for the same D4 in the presence of weak field. One value in the strong field, another value in the weak field. Therefore, their CFSE values depends on the field strengths of ligands. But in the case of D1, D2, D3, D8, D9, D10, they will show the similar CFSE values in the presence of a strong field as well as in the presence of weak field. Therefore, their CFSE value is independent on the field strengths of ligands. So this is a major important. So next after this, we have one question now. For example, for a complex compound CrH2O taken 6. Actually, in a complex compound CrH2O taken 6 square bracket plus 3. For a complex compound pairing energy is 23,500 centimeter inverse. Pairing energy is 23,500 centimeter inverse, and delta naught is delta naught. This is the crystal field stabilization energy. Crystal field stabilization energy for octahedral. Octahedral complex is the delta naught. Octahedral complex is the delta naught. It is 12,600 centimeter inverse. And the naught is 12,600 centimeter inverse. So find CFSE and electron configuration. CFSE and electron configuration. So hybridization also. So how can we calculate this? For a complex compound CrH2O taken 6 square bracket plus 3, pairing energy is 23,500 centimeter inverse, and delta naught is the CFSE for octahedral complex is 12,600 centimeter inverse. So find CFSE and electron configuration hybridization. So in order to solve this question, first what is the complex compound? CrH2O taken 6 plus 3 is given. So this is the complex compound. In this H2O is what kind of ligand? It is a weak field ligand. H2O is a weak field ligand. This is. So according to the spectrochemical series, H2O is weak field ligand. So, and it is a neutral ligand. Therefore, what will be the oxidation number of the chromium in this case? Chromium is the +3 in this case. So what is the electron configuration of chromium now? 3d5-4s1. So 3d5-4s1 is the electron configuration of the chromium. But in chromium +3, we have what kind of electron configuration now? One electron from 4s, 2 electrons from the, therefore d3 or 3d3. So 3d3 is the electron configuration now. Then what is the, so in the presence of weak field ligands, what will happen? So weak field ligands, it will be splitting into T2Z and EZ. This is the EZ and this is the T2Z. Therefore, you get this is according to what now? Hund's rule only. So presence of weak field ligand. So presence of weak field ligand, what will happen? Electron distribution taking place according to Hund's rule. Therefore, T2Z3 is 0 in this case. So T2Z3 is 0 in this case now. T2Z3 is 0. Therefore, CFSE is what now? CFSE is equal to minus 0.4 into T2Z electrons plus 0.6 into EC electrons into delta naught plus pairing energy now. So this is our principle. So minus 0.4 into T2Z electrons are how much now? 3 electrons plus 0.6 into 0 into delta naught. And is there any 2 electrons in this case now? Therefore, no 2 electrons in this case. Therefore, number of electron pairs 0. Therefore, 0 into P. Therefore, it is equal to minus 1.2 delta naught. Minus 1.2 delta naught, it is the CFSE. And what will be this is the electron configuration, T2Z3 is 0 in this case. And also, what will be the purpose of this? Here, this is given now. So, pairing energy is 23,000. Pairing energy is the 23,500 centimeter inverse is given, and delta naught it is less than that one, 12,600 centimeter inverse. Here, what pairing energy is lower than the delta naught is lower than the P. Therefore, this will happen in the presence of weak field or not? Presence of weak field ligand. Therefore, this H2O nature can be determining using this P and delta naught. P is the pairing energy, delta naught is the crystal field stabilization energy for the octahedral complex. So by seeing these two values, delta naught is lower than the P. This will happen in the presence of what are weak field ligands. In the weak field presence of ligands, electron distribution generally taking place according to Hund's rule. Therefore, you will get in the T2G3 is 0. So CFSE, our principle is what now? Minus 0.4 into T2G electrons plus 0.6 into Pg electrons into delta naught plus pairing energy. So no two electrons there in the T2G lower energy. Therefore, 0 into P is the pairing energy total. So CFS is equal to minus 1.2 delta naught. So therefore, this is the one question. For example, one more, that is for an octahedral complex. For an octahedral complex, delta naught is 21150. What is delta naught? This is 21150 centimeter inverse. And pairing energy is it is more than this one. So 27750 centimeter inverse. Then what will be the nature of this complex compound? So nature of this complex. Here what will be the observation? So delta naught is lower than the pairing energy. So it is given in this case. So delta naught, it is what? 21150. This is pairing energy is more. Delta naught is very less. Delta naught is less, pairing energy is more. If delta naught is lower than the pairing energy, what will happen? This will happening in the presence of weak field ligands or not. So this is presence of weak field ligands. So complex compound is present at the presence of weak field ligands, and electron distribution will taking place according to Hund's rule. This is the nature of the complex. For an octahedral complex, delta naught is lower than the pairing energy. That means presence of weak field ligand. So complex compound, octahedral complex compound is present the presence of weak field ligand. So this is the presence of weak field ligand. Usually you will getting what the high spin. So this is the nature of complex. High spin. The nature of the complexity. This is the nature. So presence of weak field ligands generally or usually you will have the single electrons, more number of single electrons. More number of single electrons means high spin. So this will happen in the presence of weak field ligands because delta naught is less than the pairing energy. If delta naught is less than pairing energy, delta naught. So the energy gap between the higher energy EG and lower energy T2G is very less. Therefore, no pairing will taking place. If energy gap between the higher energy EG, lower energy T2G in case of octahedral complexes, no pairing will occur because pairing energy is more. Therefore, no pairing will taking place. So therefore, delta naught is less than the pairing energy. So one more question now. For example, so the pairing energy of cobalt plus 3 ion is pairing energy of cobalt plus 3 is 50 kilojoules per mole. 50 kilojoules per mole. And delta naught for the complex. Delta naught for the complex. CO energy taken 6 plus 3. CO energy taken 6 plus 3 is 275 kilojoules per mole. 275 kilojoules per mole. Then what will be the magnetic nature and CFAC? So find the magnetic nature and CFAC values. Find the magnetic nature and CFAC now. So actually pairing energy is how much now here? Pairing energy is 250 kilojoules per mole. Pairing energy is 250. Delta naught, this is the stabilization energy for the octahedral complex is 275. So by seeing these two values, so what will happen now? Delta naught is greater than the pairing energy. If delta naught greater than the pairing energy, electrons tends to fail in the lower energy T2Z. If delta naught is greater than the pairing energy, this will in the presence of what now? Strong field ligands. Strong field ligand. So NH is a strong field ligand. It is also there in the complex. Delta naught is greater than the pairing energy, presence of strong field ligands now. So this will, if energy gap between the higher energy and lower energy, it is more. Therefore, pairing taking place in the lower energy. So what will be the electron configuration of cobalt now? The CONS3 taken 6 square bracket plus 3. So what will be the cobalt is the plus 3. Cobalt is the plus 3 because NS is the neutral ligand. So cobalt is the plus 3 in this case now. So cobalt electron configuration 3d7 4s2. Actually cobalt is what now? Cobalt 3d7 4s2. 3d7 4s2. So cobalt plus 3 means what now? 3d6. So cobalt plus 3 means 3d6. 3d6. So presence of strong field ligand, what will happen now? 3d6. So the crystal is splitting taking place. So in the 1, 2, next is this is the 1, 2, 3, 4, 5, and 6. So T2G6 is 0. T2G6 is 0. So is there any unpaired electron? So number of unpaired electrons 0. Number of unpaired electrons 0. Therefore it is a diamagnetic. So magnetic nature is a dia. And what about the CFAC? CFAC it is equal to what? Minus 0.4 into 6 plus 0.6 into 0 to delta naught plus pairing energy. So minus 0.4 means 2.4. Minus 0.4 into 6 is a 2.4. This is 0. Delta naught. So pairing energy is how much now? Pairing energy is given. So pairing energy, number of unpaired electrons, number of 2 electrons in a single orbital is the 3. 3 into P. P pairing energy is how much now? 250 kilojoules. So this is 250 kilojoules per mole. So this is the what now? CFAC it is equal to what now? How many T2G electrons? 6 T2G electrons. These electrons are 0. Therefore, my CFAC is equal to minus 0.4 into 6 plus 0.6 into EZ means 0. EZ electron 0, T2G electron 6 minus 0.4 into 6 plus 0.6 into 0 into delta naught plus pairing energy. So pairing energy is equal to M into P, where M is the number of paired electrons. How many number of paired electrons now? 3 are paired electrons. So 3 into P. 3 into P. P is already given. That is 250 kilojoules per mole. So therefore this is minus 2.4 delta naught. So delta naught is also given. That is what now? That is minus 0.4. What is delta naught now? Delta naught it is minus 2.4 into delta naught. This is the 275. So 275 kilojoules per mole plus 3 into 250 kilojoules per mole. So this is the total CFSC for this complex. So pairing energy is given. How much it is given? 250 kilojoules per mole. And delta naught also given, that is 275 kilojoules per mole. to find what now magnetic nature of the compound as well as CFSE. So pairing energy and delta naught. So pairing energy, by seeing these two values, pairing energy is lower and CFSE is higher. So if delta naught is greater than the pairing energy, this will happen in the presence of strong field ligands, and electron distribution taking place against to Hund's rule. Means in this complex compound we have what now? Cobalt is the +3. Cobalt plus electron configuration 3d6 or d6. So all these d6 electrons filling taking place against to Hund's rule. 1, 2, 3, again 4, 5, 6. This is the way to fill in the electrons, the lower energy orbitals. So number of unpaired electrons 0 now. So these are 2, these are also 2, these are also 2. Number of unpaired electrons 2. Therefore it is diamagnetic. CFS is what now? Minus 0.4 into P2G electrons. P2G electrons 6 plus 0.6 into EG electrons 0 into delta naught plus pairing energy. Pairing energy is equal to what now? M into P. So pairing energy is equal to M into P. So pairing energy is given now. This is 250 kilojoules per mole. This is 250 kilojoules per mole, and this is what now? M. M is what now? Number of 2 electrons in a single shell. Number of 2 electrons in a single shell. How many there are? This also have 2. This also have 2. This also have 2 now. There are 2. There are 3 subshells with 2 electrons. Therefore, how many? M is equal to 3. 3 into P. So minus 0.4 minus 2.4 minus 0.4 into 6 plus 0.6 into 0 plus delta naught plus pairing energy. So this is minus 0.4 into 6 means minus 2.4 delta naught plus 3 into 250 kilojoules. But already delta naught is also given, that is 275 kilojoules per mole. So this is the story about the crystal field splitting in octahedral complexes. Now we are going to discuss the next. It is crystal field splitting in tetrahedral complexes. Crystal field splitting. Crystal field splitting in tetrahedral complexes. In tetrahedral complexes. Tetrahedral complexes. What will be the general formula of the tetrahedral complex? So Ml4 plus or minus. Ml4 plus or minus the tetrahedral complex formula. So tetrahedral compound generally we can representing Ml4 plus or minus N. L is the ligand, M is the central atom, and plus or minus N is the charge. So what will be the shape of this Ml4? So Ml4 plus or minus N, this can be written as what now? This is the 3D form of the Ml4. So there are how many ligands there in this now? There are only 4 ligands. There are only 4 ligands. There are only 4 ligands in this central atom. So this is the ligand. This is the one ligand. So all these 4 ligands occupying 4 alternative. This is the ligand. This is the alternative position. This is the another ligand. Second ligand. This is the after the alternative one. This is the ligand. So after this we have what? This is the ligand. So therefore these 4 are connecting. This is the Ml4 plus or minus N. This is what now? This is the tetrahedral complex. This is the geometry of the tetrahedral complex. This is the geometry of the tetrahedral. Geometry of the tetrahedral. Tetrahedral complex. So this is the ligand. After one empty, then ligand. After one empty, then ligand. After one empty, then one ligand. After one empty, one ligand. After one empty, one ligand. After one empty, one ligand. So this is the Ml4 plus or minus A. So the d orbitals. This is the only metal with connecting with the 4 ligands. Actually, M plus 4 ligands is getting the Ml4. Ml4 plus or minus Ml. This is the formation of the Ml4 plus or minus in complex, that is the tetrahedral complex. So in this, we have the d orbitals of the central atom. When metal ion is dissolved in the Ligand solution, there will be a splitting of d orbitals. So here, what about the axis? This is the x-axis. The x-axis. This is the z-axis. The z-axis. The x-axis, and this is the x-axis. This is z-axis, and this is the y-axis. This is the y-axis. So x, y, z axis now. So geometry of the tetrahedral complex, these four ligands. In Ml4, there are four ligands. Their four ligands are occupying four corners of the tetrahedral geometry now. So those four ligands are occupying four corners of the tetrahedral, but alternative positions. Ligand, one vacancy, one ligand, one vacancy, one ligand, one vacancy, and one ligand. Okay, so there are four ligands. These four ligands are occupying four corners of the tetrahedron. And now, this is the metal. So metal having d orbitals and ligands approaching to this metal. So ligands and metal. So the d orbitals which are oriented, the d orbitals which are oriented, in between the axis. In between the axis, they are T2Z set. Experienced greater repulsions. Experienced greater repulsions from the ligands. Greater repulsions from the ligands. Ligand or ligand field strengths. Ligands field strengths. Because T2Z set of orbitals, their lobes are present in between the axes. Their lobes are present in between the axes. But here, there is no ligand is present on the axis in case of Ml4 tetrahedral geometry now. So this is the ligand is not orienting along the XYZ axis. This is the ligand is not orienting along the XYZ axis. This is the ligand is not orienting along the XYZ axis. This is the ligand is not orienting along the XYZ axis. But all the ligands approaching to the d orbitals of the central atom in between the axis. In between the axis. The d orbitals which are oriented in between the axis, they are T2Z set of orbitals experienced greater repulsion from the ligands or ligand field strengths. Therefore, their energy increases. Their energy increases because of electrons of the ligands. Electrons of the ligand means lone pair electrons of the ligands and d orbital electrons of the metal atom. D orbitals of the metal and ligand electrons. Ligand electrons, they are orienting or they are approaching in between the axis. That's why there will be a greater repulsions, therefore their energy increases. Whereas the the d orbitals, which are oriented along the axis, that is easy set. That is easy set of orbitals. Easy set of orbitals experienced lesser repulsions. Experienced lesser repulsions from the ligands. Therefore, their energy decreases. So, therefore, the 5d degenerate orbitals splitting in this way. So 5D degenerate orbitals. These are the 5D degenerate orbitals. Fitting in this way. So the d orbitals which are oriented in between the axis, they are EZ, and these are T2Z. So the T2Z set of orbitals generally they are oriented in between the axis, in between the axis, and ligands in the tetrahedral geometry also approaching in between the axis. Therefore, there will be a greater repulsion between them. Therefore, their energy increases. Therefore, their energy increases. So the energy gap between them it is it's a delta naught is the barycenter, and the higher energy T2Z and lower energy TZ. It is equal to what? Delta. This is the delta T. Why it is delta T now? This is a CFSE in a tetrahedral complex. CFSE in tetrahedral complex. CFSE in tetrahedral complex. And the energy between these two is the minus plus 0.4 into delta T. And this is the energy between lower energy EZ and the barycenter. It is the minus 0.6 delta T. And CFSE for this it is CFSE for the tetrahedral. It is the delta T. So delta T it is equals to the lower energy minus 0.6 into delta T minus 0.6 into EZ electrons plus 0.4 into T2Z electrons to delta T. Again, we have the pairing energy. So pairing energy. So where pairing energy it is equal to M into P, where M is the number of paired electrons. And P is the pairing energy. This is the total pairing energy. So total pairing energy is equal to M into P, where M is the number of paired electrons, P is the pairing energy. So CFSE in case of tetrahedral, that is delta T, it is equal to minus 0.6 into EZ electrons plus 0.4 into T2Z electrons plus delta T into T, the pairing energy. Actually, in case of octahedral complexes, splitting is due to what? Octahedral complexes, splitting is due to 6 ligands. Splitting is due to 6 ligands. Whereas in the case of tetrahedral, tetrahedral complex, splitting is due to only 4 ligands. Therefore, which one is higher now? So delta naught is greater than the delta T. This is the splitting energy in case of octahedral is greater than the splitting energy in the tetrahedral. Because splitting energy in case of octahedral complexes is due to 6 ligands, whereas in case of tetrahedral complexes, splitting is due to only 4 ligands. So the relation between them it is what now? Delta T is equal to 4 by 9 into delta naught. 4 by 9 into delta naught, or 9 delta T it is equals to 4 delta naught. Therefore, which one is higher now? Delta naught is higher than delta T. So delta T is equal to 4 by 9 delta naught, or 9 delta T is equal to 4 delta naught. Therefore, delta naught is higher. This one is higher and delta T is lower. Because delta naught is due to 4 ligands. Delta naught is due to 6 ligands. Delta T is due to 4 ligands. So this is the splitting in tetrahedral complexes. Now, crystal field splitting in Square planar complexes, square planar geometries, square planar complexes. So square planar complexes also we have the ML4. ML4 is the ML4 plus or minus n is the complex compound composition is the ML4 plus or minus n. But actually in ML6, so this is the ML6. In ML6 there are 4 ligands in one plane. These are the 4 ligands in one plane, and these 4 ligands approaching to the central atom along the xy axis, and there are 2 more ligands. There are 2 more ligands. One is above to the this plane, and another is below to this plane. So this is ML6. ML6 plus or minus n. This is the octahedral complex. By removing 2 ligands along the z-axis, by removing 2 ligands along the z-axis, we are getting the square planar. This is the square planar. This is the square planar. So all the 4 ligands are occupying the 4 corners of the square. This is the square planar. Therefore, so actually, what will be the crystal field splitting in octahedral? So octahedral crystal field splitting, it is like this one. This is the D 5D degenerate alpha splitting into 2 energy levels. One is the lower energy, the T2G, and higher energy is the EG in this case. This is the T2G, this is EG. This is the delta naught. But in case of square planar, by removing 2 ligands along the z-axis, what will happen now? So ligands which are oriented in between the axis. The ligands which are oriented, these are the 4 ligands are oriented along the xy axis. This one. These are the oriented along the xy axis. Therefore, dx square y square is this ligand. This is what now? This is y-axis. This is the x-axis. So this is x-axis, this is y-axis, but this is the z-axis. Okay, so ligands which are approaching the d orbitals of the central atom along the xy axis. So the d orbital which is oriented in between the xy axis is the dx square y square. Therefore, their energy is increasing in this case now. But 2 ligands are not appearing in the square planar geometry. Therefore, this in case of square planar geometries, this will be, this is the dx square y square. This is the dx square y square, and one is the dz square. Energy is decreasing because no ligand is present along the z-axis. No ligand is present along the z-axis in this case. Therefore, their energy, it is decreasing in this case. This is the dx square y square. But in this presence we have what now? One dxy now. Suppose this is the x, this is the y. So in between we have what now? Dxy orbital of the central atom. Dxy orbital of the central atom. The dxy orbital is near to these 2 ligands. Therefore, their energy somewhat increased. Therefore, in this case, we have what now? This is only we have what here? Is the d yz and dzx. But one more, that is this is the dzx. This is there are 3 dxy, dyz, dzx. So dxy orbital is nearer to the ligands now. So that's why their energy increasing about to the dz square. This is the dxy. And remaining what now? They are dxy, dyz, and dzx. So this energy gap between the higher energy dx square y square and the lower energy dxy dzx, it is the delta square planar. Delta square planar. So which is higher than the delta naught. This is the energy gap between the higher energy Eg, lower energy T2Z is the delta naught. So delta naught is lower than the delta square planar. And already we seen delta T is very lower than the delta naught. Therefore, delta T is lower than the delta T is lower than delta naught, and delta naught is lower than the square planar. Friends, if you have any doubt, please ask.